So we have seen the kind of erosion, these are all just typical pictures you see, cutting off of the roads, buildings, hotels, valuable properties being dislodged by the waves that create or cause coastal erosion. This is a very short movie or a video clip which shows the erosion in progress, so particularly during a storm, and you can see by yourself what is going on there. So we know the devastating effect. So many times what happens, this erosion can be some kind of a short term, only for some time, okay, and it can be either gradual or all of a sudden, understand. So but one thing you should remember is, whenever you plan to have a structure in the coastal area, you have to look for this kind of effects on the adjoining shoreline. Now when you put a structure, what happens on the adjoining shoreline? So now we see the problem. In order to go in for the coastal protection, etc., we will try to understand how this erosion takes place, coastal erosion, how it takes place. So under this I will try to explain this phenomena with the help of this slide, particularly when there is a storm that attacks a coast. You know that the tidal variation, you know about the tidal variation. So initially you have the mean low water, then you have the mean sea level somewhere here, above which you have the mean high water line. Under the mean sea level, that is in between the MLW and MHW, you see the waves will be propagating and breaking, and it will be breaking at a location when the wave height is approximately 0.78 times water depth, all of us know. So that 0.78 times water depth may be occurring somewhere here. So once the wave is breaking here, then you have just the uprush. The same thing when there is a high water, when there is a mean high water, it will be breaking somewhere here, and then after that you have the run up. So what will happen is, there will be some amount of sand which will be removed, transported, okay, and then it will be brought back. So you will see that when there is over the beach, there is sand which is going up and again which will be coming back. So this kind of oscillation, and during such an oscillation, if the material is moving without much of loss of material, then the beach is said to be in stable equilibrium. Even if you see some kind of erosion taking place, what will happen is, this will remove the sand, and then probably this sand will settle something like a bar, and then again this bar will be removed during low tide, and this sand will again redeposit. So this is one kind of a problem which you need to have in mind, whether it is a short term kind of erosion or a perennial kind of an erosion, etc. Now in this case, when there is a storm, the water level in the ocean will go up. When the water level in the ocean goes up, it may go even above the mean high water. How many high waters you have? In a day you can have either one high water or two high waters, depending on the kind of tidal variation. So over a year if you take, you will have mean high water and also you will have maximum high water, that is clear. Now when there is a storm, the water level in the ocean can go even above the maximum high water, but definitely it will go most of the time it will be higher than the average high water line. Under that situation, the water level has risen in this case as shown in the second slide. When the water level goes up, the waves which were originally breaking in this particular location, that is governed by 0.78 times water depth, will not happen because at that particular location you have sufficient water depth, so that the criteria of the depth limited criteria will not satisfy. So what will happen? The waves will still propagate with all its energy stored and it will attack the coast. And when it is attacking the coast with so much of energy, part of the coast as indicated in red color will be the portion which is being swallowed. The material will be removed. How much of material is going to be removed depends on the kind of energy the waves contain and the kind of material that is lying on the beach. So the material is removed. And when it is removed, where does the material go? Naturally it has to go inside the ocean. So all this material will be removed gradually, and then as the storm persists, the cumulative effect of the erosion will be there, and you see greater portion of the coast will get eroded as shown here. So all this area will be eroded and this sand is likely to be towards the seabed. So this is a problem that has occurred all of a sudden, and if you have some kind of structures and these structures, the stability of these structures are rather questionable. So now the storm recedes, it settles down. The original scenario comes into picture. The original scenario is this one, which is corresponding to the first one. Under such a situation, what will happen? When the waves are propagating, you know the effect of orbital motions, you know the effect of mass transport velocity. So the sand in the seabed will be removed and the sand will be directed towards the direction of propagation, which will be towards the coast. So the sand which has been removed due to the storm is now going to get settled back into this eroded area. This process will continue for some time. So now if the quantity of material that was removed during a storm and deposited here is again redeposited to the eroded area without any loss, then what do we say? The coast is said to be in equilibrium. There is not much of a problem. even during a storm this has removed the material, but it has come back. We have a classical example later when I talk about the tsunami. This has happened when we really monitored about the performance of the shoreline. So now you see that if there is no replenishment back after the storm, you see that the stretch of the coast gets eroded. This is the way it has been explained in the coastal engineering manual very clearly, and for benefit for additional information you can see this book, this is a manual by US Army Corps of Engineers. So now we have understood how and why you have the coastal erosion when you have a storm. But then we should also know how the sand which is lying in the seabed comes to the surface along the beach. That is very important. But we have undergone the course on wave mechanics, and you know, all of us know the physical behavior of ocean waves. What does that say? That says in deeper waters you have no effect of the surface waves on the seabed. So that means the sand in the seabed in the under this location will be more or less stable. But once the waves leave the deep water situation, once it enters the intermediate depth conditions, you know that it starts feeling the bottom, and the horizontal displacement will slowly reduce as you go towards the seabed, but still the effect of waves will be felt on the seabed in intermediate water depths. And at that point of time you see the initiation of sediment motion coming into picture, which we have seen recently. Depending on the relationship between the wave characteristics and the size of the sediments, the sediments in the seabed will get its effect and it will start moving. And when it is moving, it is going to now feel the effect of the mass transport velocity. What does the mass transport velocity do? The phenomena of mass transport velocity is some amount of mass is being transferred in the direction of wave propagation. So the sand which is picked up from the seabed is now subjected to motion, gradual motion in the direction towards the coast. So now you see the mass transport velocity is now going to be a function of z. Okay, recollect the expression for mass transport velocity. If you recollect, we have seen that mass transport velocity will be a function of z and it will be a function of HL square. Function of HL square. That means when do you expect steepness to be higher? When you have storms, cyclones, etc., the steepness of the wave is expected to be higher. At that time you can expect more amount of sand being propagated towards the coast. Okay. Now, so there will be motion in this direction and there is a velocity gradient also. So you see the motion will be taking place and all these things will reach your breaker zone. So now you see the sand which was in the seabed is picked up by the particle displacements of the wave being transmitted in the direction of wave propagation by the phenomena of mass transport velocity, and the sand will reach a breaker zone somewhere near the breaker zone. And at the breaker zone what happens? The wave will break depending on the breaking criteria. When it breaks, the sand is now set in a motion, it undergoes a churning motion because the wave is going to break. Okay. So, the sand will get sorted out. Okay. So, sand will get sorted out. You have both fine sand as well as the coarse sand. It will have kind of a mixing. So, the sand is now coming to the surface and now it is being transmitted. So, it is being transmitted to the coast, to the shoreline. So, now you see there is a region where the sand is going to move, and what is that region? That region is nothing but the surf zone, the distance between the shoreline and the movement of the sand along the shore will start somewhere near the breaker zone. Okay. That is where it is really brought to the surface. When it is brought to the surface, then you have this area sand in suspension and sand moving as bed load also. Sand will be moving as bed load as well as in suspension. So, most of the sand is now within the surf zone. Now, this is as far as with the help of an elevation. Now, we will look at the from in plan. Now, what we have understood right now is how the sand from the seabed has come to the surface somewhere near the breaker zone, that is very clear. Then what happens? How the sand moves? So, this is in plan, wherein you have the, when you look into the ocean, there will be locations where the waves will be coming either this direction or in this direction. For a location, for certain location it will come directly to you, that is directly normal to the shoreline. When you have a oblique attack of the wave, and when it reaches somewhere near the line of breakers, what will happen? At the line of breakers, when the waves break and when the waves are in a direction, it will have two components. Naturally, when it is inclined, it will have two components. Since it is inclined, this will have a component along the shore and normal to the shore. When the waves break, because of the waves breaking, we have currents set in. Current is nothing but the movement of mass of water that is going to be created because of the waves breaking in the breaker zone, and this current is nothing but the wave induced current that will start somewhere near the breaker zone, and it will be directed along the shore as well as normal to the shore because of the oblique wave attack. Is that clear? So, the flow field or the speed with which the water moves along the shore is called as the longshore currents, and the one which is moving normal to the shore is called as what? Cross shore currents, or it is also called as onshore offshore currents. So, you see that we have a system of currents in the near shore I have already explained about the rip currents that is also going to take place near the in the near shore zone. Okay. Now we have the longshore currents and the onshore offshore currents, and these two currents will act as the driving force in moving the sediments. So hence the sand within the surf zone will be moving along the shore as well as normal to the shore. But along the shore is much more, usually it is much more compared to the onshore offshore currents. So now you see that there is a continuous propagation of ocean waves, a continuous system of breaking of waves, and continuous generation of longshore currents. Hence there is a continuous motion of sand along the shore. Is that clear? Now through these slides it is clear how the sand is picked up and how it is transported. We understand clearly that the sand is going to move along the shore. With this background, wherein we have understood what is the mechanics of sediment transport, this longshore currents are also termed as littoral currents. And the movement of sand along the shore, along the coast, is called as, we refer this as littoral drift or longshore sediment transport. So the movement of sand along the shore is called as longshore sediment transport, and the movement the currents are called as littoral currents or longshore currents, and it is also referred to, this is also referred to as littoral drift. So later we will try to work out some few examples how to estimate the littoral drift quantities, etc., direction, quantity of sediment transport, etc. So what? The sand is moving. So what? When the sand is moving, naturally it is going to dictate the coastal geomorphology, the orientation of your coast, the changes that can take place along the coast. So coastal geomorphology, coastal morphology is extremely important, and that is what we will try to understand. This is in brief about coastal morphology, the physics behind the whole thing. Sea waves, when they propagate, they have the shallowing effect over the, when they propagate over the foreshore. The definitions of the foreshore, backshore, etc., we have already seen earlier. This foreshore shallowing, you can have frictional drag because of the bottom depth contours, and also a certain amount of energy can be dissipated. So if you have energy dissipation taking place before the waves reaches the coast, for example, if you have a coast and you have some kind of an artificial reef, sorry, not artificial, some kind of a natural reef, some kind of a natural reef, and now you have the waves propagating. What will happen in this case? If there is no reef, the wave is supposed to break somewhere here, and that is going to create erosion. Now, because of this existence of a natural reef, the energy can get dissipated. So, when the energy gets dissipated, higher energy to lower energy, so the sand will automatically get deposited here. When such a situation happens, you have a beautiful beach. So, herein we talk about dissipation or dissipators, we think of dissipators. So, that is one area, one kind of area where you should think when you want to plan for coastal protection. How can I reduce the energy before it reaches the coast? So, when you see that, if you are able to see that all the energy is dissipated, then the coast is said to be more or less stable. No changes until the wave energy changes, equilibrium, so coastal morphology is going to be constant. So, we do not have a coastal engineer, does not have any role to play here. So, using this, there are some attempts where you can think of having a structure, these are called as submerged breakwaters, which we will be seeing under the topic when I cover on breakwaters. So, you can think of having submerged artificial structures in order to dissipate the energy, so as to combat coastal erosion by dissipating the waves. On the other hand, energy remains in the wave, then it is a problem. So, when you have energy remaining in the waves, then sediment, there are two situations that can arise. Sediment resistance is greater than sediment resistance is greater than erosive force, and sediment is less than erosive force. If sediment resistance is greater than erosive force, then no sediment is removed, further loss of energy. So, because of this, it will result in deposition, and just vice versa will happen when the, if you have the sediment resistance less than erosive force, your sediment will get automatically be removed, because the resistance is less, and when it is removed, then naturally you are supposed to have erosion taking place. So, erosion or deposition will naturally result in changes in the coastal morphology. So, this beautiful slide clearly explains for us what are the problems or what are the main causes where you should look for if you see a coast is getting eroded. This gives a overall picture. Now, we move on to coastal budget, coastal sediment budget. First, I am trying to explain to you all the terminologies and all the physical parameters and physical phenomena that are involved in the coastal zone and in the area of coastal erosion. First, we will understand that, and then we will go in for the mathematical aspects of estimating all these things and how do you use all these calculations, etc. When you talk about sediment budget, See, like what we have our own budget, right, what is in and what is out and what is that you have, that is a simple budget. So, here also we have natural and anthropogenic. You look at the arrows, one is sink and one is source. So, now what are all the things that are going to come inside the sediment budget? From coastal dunes, tidal flats, marshes, etc., you can have some amount of sand coming inside the coastal area. Then from the offshore, if you have cliffs, from the cliffs there can be some sand, there is also some amount of sediment supply. Then longshore sediment transport or the longshore drift, you are going to have some amount of sand coming into the pool. Then through beach feeding and also through dune building, all these things are adding on to the sand, that is income inside the system. The outgoing can be during storms to the offshore or to the coastal stores, there can be some movement of sand away from the source. Then estuarine sedimentation, there can be some amount of sand which are moved from the ocean, transported through the estuary, and that sand does not come inside the ocean. So, that creates another major problem, that is when you have an estuary and open to an ocean. So, there is a supply from the ocean during high tide, it brings in lot of sediments, but during the low tide when it is returning back, it does not take away all the sand, it leaves the sand here. And if you allow this to continuously happen, what will happen? There will be a lot of sand accumulating here, and ultimately it might lead to the closure of the river mouth. That is going to create another headache, another problem. So, you see some that to offshore during, so this is estuarine. So, again littoral drift out, although you have some sand coming in, all the sand are not going to remain in one location, it can go away. Or land claim, then beach mining or dredging, these are all removal from the sand from the location. So, you see that when you are talking about sediment budget for a coast, you have to identify all these problems, how much of sand can be expected to come into this area, how much of sand is going to go from this area, etc. So, this needs a proper planning. Now, we again will start with what happens when you have sand moving along the coast. Here is a slide which shows, for some reasons you have structures penetrating into the ocean, and these structures can be normal to the shore, harbor breakwaters, groins, or you need a structure to support a pipeline for continuous drawal of seawater, maybe for aquaculture or power plants. So, there are so many industries, etc., which may need the continuous seawater, and they will be mounted on structures as shown here. These structures can be some kind of trapezoidal section, it can be some kind of a trapezoidal section, jetting into the ocean. Okay. And if this structure is either impermeable or slightly permeable, what will happen to the shoreline? As we have seen earlier, there is a continuous movement of sand along the shore. When it is moving along the shore, you have put us, if there is a structure normal to the shore, what will happen? This structure is not going to allow the sand to move, and hence you will have the advancement of the shoreline and you have the beach advancing. So, you have nice beach here. This process will keep on continuing until it reaches a stage when you have a, when it reaches this location, then you have automatic bypassing. Is it advantageous or disadvantageous? So, putting a construction, you see that you have a beach on the updrift side. So, we call this as updrift side and this side we call it as downdrift side. So, this is very clear. On the other side, on the downdrift side, what is going to happen? You know the phenomena of diffraction. What is meant by phenomena of diffraction? When the waves move, it penetrates into the sheltered area. It penetrates into the sheltered area, and because of the energy contained in the waves, this will remove the sand. When the removal of sand takes place, the sand is available for the longshore currents to drive it, because at this location also the waves are going to break, at that location also you have the longshore currents, and that is going to move the sand along the shore. So, you see the phenomena of diffraction permits the wave to propagate into the sheltered area, remove the sand, and then comes to shore and then comes to the surf zone, and then the longshore currents keeps driving the sediments. So, now you see, by having a single groin, you have the advancement of the shoreline on the updrift side and erosion on the downdrift side. This is universal problem, wherever you construct, this is what is going to happen. But can we stop construction of structures? For some reason or other we might need the structures. Which is the one which is really governing the direction of littoral currents or littoral sediment transport, littoral transport or the sediment transport. So, when you are dealing with the sediment transport, it is not only the magnitude which matters, it is also the direction which is very important. Of course, the direction is going to be governed by your basic Snell's law, it comes only from your refraction. So, this point is very clear now. So, even natural promontories, natural headlands, you may have a nice coast, but you see this is along the Visakhapatnam coast. So, if you have a straight beach, then there may not be any problem. Okay. Suppose if you have the coast itself is moving like this, you have a large promontory. In this case you will see, and it is along the sandy coast, then you will see that this area is expected to be associated with formation of beach, and on the other side they might be having some protection measures or trying to fight with the coastal erosion. That is, if in this case the sand is moving in this direction. Okay. If the sand is moving in this direction, you see that an opposite trend will occur. So now imagine if you have a river and you have the ocean, and if the sand is coming and depositing here and closing the river mouth, naturally you will think of some kind of an obstruction. And if you are very sure that the sand is mostly 100%, it is moving in this direction, then what will you do? What is the kind of a protection measure you can think? You can construct a training wall here. So what do? You prevent the sand coming and depositing here, and you will have the beach here. But if it is seasonal, during the other season there can be sand moving in this direction. What will happen to that sand? It will come and deposit here. So you try to put another wall here. If the direction both the directions are almost of same kind of amplitude, then you have same length of training walls. You understand? So here this is what we need. Suppose if you do not know about the direction and by chance in a location where the direction of sediment transfer is predominant in this direction and there is only very little transport in this direction, and you have raised a training wall in this way in order to serve as a protection measure for this river mouth, that is not going to happen. It is going to, your solution is going to aggravate the problem. So you are going to have more sand deposited. So although the solution is quite not so difficult, but it is a bit tricky because you need to have, most important, the knowledge on the sediment transport, particularly its direction apart from your quantity. Is that clear?